Okay, so thanks for the introduction. I'm not sure what to say. Yeah, I'll start with superconductor. I agree we're living in the second quantum revolution. And so why am I excited about the next few years? I'm going to try to, in this short period of time, give you a sort of a summary of what I think can happen. Sorry. Okay, we're all here because we believe that quantum computing basically has some problems that will be easy on a quantum computer that will not be on a classical computer. Fundamentally, it changes what we mean by compute. Problems that, most famous of them, factoring or even simulating chemical reactions, materials, there's many of the examples along these lines. But essentially, we know of many algorithms out there that if we can solve, once we get a quantum computer that's big enough, if we can solve them, we'll not be able to do them on it appears we will never be able to do them on a classical computer. So think of quantum computing as the only technology that breaks that. At IBM, we have a roadmap. I'm not going to go through the details of this roadmap too much other than say a couple of things. First, we're very proud of the fact that we've hit every milestone since we made this roadmap public. So in 2019 to 2024, I didn't update this roadmap. Yeah, sorry. To 2024, we've hit all the outcomes. And one thing I want to point out is we expect over the next few years to keep increasing how many gates can be done on our systems. And that's why I sort of show in the number up the top with 5,000 to 15,000. And then you see a big jump to 100 million with Starling and 1 billion with BlueJay. That is error correction kicking in. And so we're confident that we have a path towards error correction in the later part of this decade. But this talk I'm going to focus on what are we going to do in the near term. But before we go there, essentially in a quantum computer, you can think of the thing that executes on the quantum computer we call a quantum circuit. And there's two things that matter: how many qubits and how many gates can be done. And I've just taken a summary from references of various different papers here. And you see in these shaded regions numbers of where certain algorithms, whether it's in materials, chemistry, optimization, or crypto-relevant problems can be solved. So you see that's right out there at circuit sizes that are quite large. You see the shaded region we call pre-utility. What we mean by that, if it's smaller than that region, we can simulate it on a classical computer. So where are we? So a little bit of honesty, we're actually just crossing this region at the moment. We're just getting out of what we can simulate into a new region. As I said, we have a roadmap that with Starling and BlueJay, we definitely get ourselves to do these pen and paper type algorithms that many famous algorithm researchers have researched. One of the questions we're asking is, are there potential numerical method advantage algorithms in this white region where we can start to access now? And it's not completely out of the question because there's papers like this paper by Sergey Bravi where they show that they can actually show for what we call short depth circuits, there's actually a separation between what classical and quantum for what we call a shallow or short depth circuit. This was a game that they proved, but there's been various other papers that have come out on complexity of these circuits. So the thing I want to leave you with is, at the start, if the complexity of the circuits is hard, then these are the circuits that we expect to use as our resource as we search for quantum advantage. So number one first is you have to be able to execute quantum circuits. And then second, you need to have a set of quantum circuits that there doesn't appear to be some way of being able to solve them classically. And so you can start to take this, and I like this paper. I'll give you some examples before I go a little bit more. There's a paper out of the Riken team, where they look at time dynamics of so on the top where you see the white lines, the black lines, white lines, black lines, it's like a striped material where either all the spins are down or the spins are up, and then they hit it with a dynamical equation. And if you're in one region, you find that the oscillations continue forever. If you're in a region beyond the parameter space, you find the oscillations decay exponentially. And then if you're in the critical region in the middle, you get this beating type pattern. They were able to run this type of circuit at 133 qubits with 15,000 gates, do essentially 100 flock gate cycles, so many of those down there. And they are able to go to a regime where you can't do easy numerical simulations, but at the small cases of 28 qubits, they find that the smaller systems agree. So the conclusion of the paper is that this sort of many-body physics problem, they can start to look at interesting dynamics, okay? So that's one. A second is, what if you mix up how you look at algorithms? So I said at the first, you want to start by running some type of quantum circuit. Here, I just called it U. And now imagine I also know that I'm interested in a problem where I actually want to find the ground state, be it some chemistry problem, some material problem. So is it possible to run a quantum circuit and use the quantum computer as an input into a classical computer? So in this algorithm, what we imagine is we create some exotic quantum circuit. We then find a way that for that quantum circuit, we generate samples. Now those samples are finite in size, say M samples. So we can define a new effective Hamiltonian. And the key here is this new one is no longer exponential. So if it's no longer exponential, it can be diagonalized, and we can report some energy. And it turns out, this paper was prototyped with our colleagues at RICAN again. It turns out that we can actually start to do chemistry solutions that I would argue are comparable to the best classical methods. They're getting on the same sizes of DMRG type simulations. Cleveland Clinic, Lockheed, and ourselves have extended these type of methods to even further. So what this is suggesting is now we know there's something complexity hard about those circuits. Let's use them as an input into a larger algorithm, and then we're able to start to explore it. You can even go one further. And I think this is another beautiful example for those experts in the field that know of phase estimation. Now I'm going to imagine that I'm going to create subsamples of different evolutions of the time. So now my matrix is dm times dm, so it's not exponential, but now I create basically subsamples where I have the different time dynamics, and now I'm able to diagonalize this type of problem. And if I can diagonalize this type of problem, I can actually get some of this. I have less assumptions in the first state. I basically can say if I've got enough DTs and I take it big enough, I actually know that I will converge to the right answer. So the teams were able to start to explore on that. So what this really starts to suggest in this near term is if you can start to mix classical and quantum computers together, we call it quantum-centric supercomputing, you are creating an architecture where we can start to explore, and we're getting comparable results to what we expect in classical computing. So one of the things we've said, I think many of people have heard me say that, is if together can we get quantum advantage in the next couple of years. So what I mean by that is get something that we run that is scientifically interesting, that is either cheaper, faster, or more cost-effective using quantum plus classical than classical alone. I do believe that this is going to be possible only if we start to really bring HPC. What I really mean by that is numerical experts in the classical world together with the quantum experts to start to do these interesting problems. So why are we getting confident that this will be possible? There's a few reasons. The first is everyone here, like Yonsei University, many of our partners, many people are coming with new ideas. I just put a couple of those algorithms at the start, but there are many more. And second, the hardware is actually getting pretty good. I'll give you this example. In 2023, so not too long ago, we set out to show that a noisy quantum computer can produce accurate expectation values on 127 qubits with 3,000 gates. That is outside what we call brute force, so that's outside where you can classically simulate it, and show that it can get accurate results. And I want to show you a little example. Imagine I give you this toy problem. Each one of these black boxes are going to be a different experiment. They're going to be, I'm just going to tell you it's an experiment. That experiment happens to have two parameters, an angle and a quantity that is measured on a quantum computer Z. For the experts in the audience, this is just the spin of the 62th qubit in this. This is an Eagle processor as well. So actually an older version. The one in Yonsei is better than this one. Of this, we measure the 62 qubit spin as a function of this angle. So the first thing you notice for all these black boxes, none of these lines are actually the same. They're all different. If I actually take 80% confident, I find they're all different by 20%. What I think is really, really cool or fundamental is one of these is actually a quantum computer. The rest of them are what we in the field call tensor methods. So it's not that quantum, when we say, what we concluded in this paper is we're at a point where we're beyond brute force, so there's no exact simulation of this. Every one of the tensor methods converge to a different answer. None of them converge to the same answer, and quantum is one of them. So you can kind of start to see it as a numerical tool where you can start to explore, start to use it to explore scientific applications. For the experts in the field, some of these numerical methods are new methods that have been invented, so new tensor methods, that the convergence of the method is based on converging to the experiment. So what that means is we've got at the point where a quantum computer is actually getting at the point to test classical methods of converging. And so they don't have formal convergence, but they test their convergence based on converging to the experiment. So that's one. We can start to do this interesting type of experiment. Second is users. So if you want to get good things run on quantum computers, if we plot the number of the average, so I'll plot here years down the bottom, and then I'll plot the average number of qubits people are using, okay? If we plot, since we put the first quantum computer on the cloud, how many qubits people were using, you see that it follows this weak, quadratic formula where the blues start at like 5 qubits and gets up to 13 qubits, okay? So before 2023, before the results of that experiment I just showed, I would say that even if people had access to 100 qubits, they were only using a handful of them. What has changed is, like I said, we got to the point where we can go utility. So here I've plotted all the different quantum hardware that you can find that has numbers in the public domain. In blue are the IBM hardware, and then the dotted line is what I call utility, where if you think of the number of qubits, it's either got to be above 100 qubits, above 1,000 gates. You got to be in that regime for you to be doing something that is outside doing classical. So the first is the hardware has got to that region. Second is the software has got to the point that is very performant. Just to give some numbers, Qiskit now runs, the updates means execution on the quantum computer runs about 70 times faster than it did before. We can do accurate gates up to 5,000. We've developed software that can mix classical and quantum together so we can explore those type of algorithms I said at the start. And we've got to the point that we can compile to these systems these long circuits, and we can get shorter ones that run. So the big two things that have changed is the hardware and the software. And if you put that together, what we find is the usage of these systems has spiked, where the average usage of the quantum computers now, using the latest hardware, is getting up to above 100 qubits. And this is a combination of this. This is why I'm kind of excited about this, is we've got to this point where we are actually starting to use them, where we can no longer simply simulate them. And then there's been many different papers that are published in what we call this new regime of doing large simulations. I just show a handful of them here, as well as some more here. So if we'll take a step back and say, even though we have a long-term plan of getting to an error-corrected quantum computer, and we need to, in my view, demonstrate a scientific examples of quantum advantage in the near term, what are three things that I think are required for this? What are the things that you need? First is obviously you need a system that is beyond being classical simulated. Second is you need a dedicated community of algorithm researchers. And third, you need a set of methods that can provide accurate executions. I call this error mitigation, error detection, and even correction. I'll explain what I mean by that. And this third one is, I think, the most important. Now I'll spend as much time as I can on explaining the third one. Actually, I stand corrected. All three of these are all important, but the third one is not as appreciated enough, and I'll try and explain what I mean by that. So first, I'm very proud of the fact that in Korea, we have now a system of this size. There's a picture of the Yonsei system that we just did the opening ceremony, as well as some of the other ones that are around the world. So as I said, the first is you need access to a computer that can be of this size and quality. Second is you really need this commitment of algorithm developers to explore using these machines in novel ways. At IBM, we've really focused on everything from how we start to create easy content, so courses to get started in quantum computing, as well as taking, videos to get started, as well as taking courses, as well as taking credentials to get certified. And then finally, as I said, many papers have been published using these machines. I am actually very proud of what has already been done in Korea. I actually think since the system got installed here, it is the fastest growing of using the systems that we've ever installed. That says something about the quality of the researchers, the quality of the students that want to get using it. It is actually, I'm very impressed by how fast. So Yonsei has started out really well training, getting these type of courses, and we're really seeing that pick up. And I think as we go forward, I totally, with all the partnerships that we've done, I totally see Korea being on the global stage in using it. So first, having a system, having the ecosystem of algorithms. So what is the third? So the third is, how do you trust a near-term device? Or how do you trust the output? Or how can you be sure that it's executing something that you can start to define quantum advantage? So quantum computers, at its most fundamental, is you run a circuit and you sample an output, okay? Scott Aronson has a beautiful paper that can show random circuits are actually hard to simulate. If you go a deep down, actually there's been a lot of work that is sort of showing that you can't actually verify that output. So if you want to have a problem where you sample and you want to confirm it's working, you either need to have some simple way of verifying it. That being said, there are ideas emerging now by Scott Aronson and others of how to put some type of peak in to solve the verification problem. But secondly, because this could still be noisy, some of the computational hardness starts to disappear. And for these type of random circuits, I don't accept that they are a viable demonstration of supremacy or advantage, depending on your word, because they are built fundamentally without the trust that the quantum computer is executing what the theory paper said. So what we started and what we pushed forward in this near term, and I'm starting to see it get much more rigorous, is this concept of error mitigation. And I'll try and generalize it as I go forward. So now, rather than send just one circuit, you send a circuit plus an observable, okay? Now, what happens here is now, because there's a well-defined theory, you can actually be confident that the result that is coming out of the quantum computer has error bars that I can propagate forward. The cons of it is this takes exponential time to run. Second con of it is people have pointed out that possibly polynomial classical algorithms exist. So if you've got something that takes exponential and polynomial, you might first start to be a bit worried. And the third, which is kind of one of the ones that I think needs to be explored more, is now because you contract it down to observables, the hardness of this disappears. And in the example I showed before, you have to compare it to tensor methods, and it gets harder to say. So starting with the error bars, I'm not going to go through the theory other than to say essentially the experiment consists of running a unitary, some noise happens, you recover the noise, you run the unitary, noise happens, you recover it, and there's a way that you can bound this recovery with this simple formula here, and you see it has this gamma bar to the ND that's exponential. You can propagate this all the way through to give you the error bars. And like I said, many have pointed it out to be exponential, but when you start to put the numbers in, you can take something that's polynomial, something that's exponential, and you can find that if you're doing small enough circuits that are still not up to the limit of running the algorithms that we want to run long term, but are nevertheless past the place where you can simulate them easy, you actually get numbers that allow you to actually look at it. And that's exactly what we've started to see in the last few years. What we've seen is that experiment in 2023, then 2024, we were able to take it from 2,000 to 5,000 gates and show that you could get most of the accuracy of the observables still there. And then it's not just ourselves, it's also Algorithmic Q as a company, as a research company out of Finland, where they've come up with their own ways of doing this type of, their own version of error mitigation to propagate it forward using tensor methods on just the errors so they can bound how that propagates. Kedma, which is a company out of Israel, has their own form of error mitigation where they can give you an unbiased estimate, control the errors, and propagate it through. And so you see that there's these sort of methods that are emerging that give you these error bars that allow it to propagate. Now I want to sort of show, next interesting, is you can start to think of this as a continuum from the error mitigation, where you take many runs, to many qubits, obviously a fault-tolerant quantum computer that exists. So what we argue is as we build these tools, you're going to see this continuous path, right? That you build trust into these methods to allow you to run bigger and bigger experiments. So now, error mitigation itself was rigorous, gives you error bars. Can you start to add error detection to it? Can you add ways of doing error detection? And the answer turns out to be true. So in an early paper by Sergey, myself, and a few others, we came up with a way we call Pauli checks. And what we were able to show is you could run some payload, and if you did checks just at the end, you could propagate through and post-select the output. But now what people have learned is you can start to, we call them space-time checks. Rather than just check at the end, check continuously through it. And so what I plotted down on the bottom is because there's a post-selection, you have to select when the output happens, whether you keep it. You see the difference between the write-only checks and the space-time checks. For the post-selection, you see it's like 1,000 times better if you can do this sort of space-time check. in terms of how many samples you can keep before you actually need to reject them. You find the fidelity is about 70 times better. And because you actually use less checks, there's a lot less gates that are using to do it. So this idea of putting error detection, and I'm going to show you results that we haven't actually shown anyone before, is now you can start to do ridiculously big Cliffords that you can create arbitrary graph states, mixing ideas of checks to get that trust back into the machine that allows you to create with high fidelity. So look at the green here is for 14 encoded qubits. Post-selected it's going up after around 6 checks, close to 1. But this all goes down to the red that you can even see it going up to 50 qubits for these large graph states that really start to give you a feel for ways that you could really push this into the future. And all of this is possible if you have access to the machines. You can start to explore this. So the way I kind of want to sum it up is I actually think that there's a continuous path from where we are today to where we get to many qubits to do fault-tolerant quantum computing. If you build methods based on trust, you can start to explore for those scientific algorithms. You can start to explore those scientific use cases in chemistry, biology, materials, based on circuits that you know cannot be simulated. I love this quote by Feynman Dyson that says, "Scientific revolutions are more often driven by new tools than new concepts. The effect of a concept-driven revolution is to explain old things in new ways. The effect of a tool-driven revolution is to discover new things that have yet to be explained." Where we are right now with quantum computing is we can start to run circuits that are at a point we cannot simulate them. So the question remains, how do we actually use them for searching for applications? Just to conclude, now if you've got this trust, you can start to build chemistry, machine learning, optimization, algorithms on top. Our view at IBM is to work with everyone. If you create your own algorithm, you're going to build it on top. And for example, many of these application functions are available online and remote, and some that are actually coming out that I think are quite nice is that extend the original ones by Q-Control, Multiverse, and Quinasis. These are ones by Kapil, which looks at optimization problems, and they're getting to very large size. And Quinova, which is actually a Korean startup company, has done some nice results that show that built upon these methods, they can start to do interesting chemistry-type simulations. So on that, I'll conclude and say the reason why I think advantage can happen is because of those 3 things: access to hardware, the development of a community of algorithm researchers that are dedicated to solving hard problems, and the development of tools that allow us to execute quantum circuits of a large size that we can trust the outputs. Thank you.